bottom of page 358, under the construct the understanding, I want you to make the following. You need to know your powers for this unit. So, for example, do you know your powers of 2? So on your powers chart, what we'll do across here, we will write the power here. Well, this is kind of, these are going to be our different bases. 2, then 3, then 4, then 5, then 6. We could do 9 as well. Do you know your powers of 2 for 2, 3, 4? So if you were square things, then cube things, then to the power 4, to the power 5, to the power 6, power 7, and so on. What is 2 squared? 4. What's 2 cubed? 8. 2 to the 4? 16. Do you see they're just doubling? The powers of 2 are really easy. And so because they're really easy, you get lots of questions with the powers of 2. In fact, you can be expected to know as many powers of 2 as possible because you just have to double them. So that can be on a non-calculator part. So this powers chart is important for non-calculator questions where you have to know your powers. You don't need to know your powers if 3 is high. You need to know 3 squared, 9. You need to know 3 cubed, 27. 3 to the 4, 81. And sometimes you might have 243, but you probably rarely get 729, 3 to the power 6. Okay? As we go to higher bases, okay, and just so that, oh my. So we can keep going. Just how did we get this number? Right? This is the base. These are all the bases here. These are all the powers here. So this is 3 to the power 4 is 81. So that's where that number comes from. For powers of 4, you need to know 4 squared is 16. You need to know 4 cubed is 64. Sometimes 4 to the 4 is 256, appears not very often, because it's also 2 to the 8. For 5, you need to know 5 squared and 5 cubed. For 6, usually just need to know 6 squared. Not very often does 6 cubed come up. And same thing with the bigger numbers. So for mental math, these are the numbers that you need to know as far as solving questions with powers. And this powers chart can be very helpful in that, because you need to be able to recognize if you have the number 81, well, 81 is 9 squared, but it's also 3 to the 4. So now if we move forward to example 1, we can highlight here what is an exponential equation. It contains a power, and there's a variable in the exponent part. So you'll get a question like this. 3 to the x equals 81, and that's where your powers chart is helpful. You go to your powers chart. Where do I have 81? When I have a power of 4. So x has to be equal to 4. So when we get to our first example here, the strategy that we're going to use is we are going to try to write both sides with the same base. So here's our strategy. We're going to write all the powers with the same base. So you go to your powers chart and you look, is there any column that has both 4 and 256.
Would Seth Christian please report to the office for an important message, please? Seth Christian, please report to the office for an important message.
Which column has both 4 and 256? 4 has it, right? Because you can write 256 as 4 to the power 4. Now, we haven't quite written both sides with the same base because the one on the right is 1 over 4 to the 4. Do you remember what exponent law would allow me to move this 4 to the top? A negative. 1 over 4 to the 4 is the same as 4 to the negative 4. Then, once you've written both sides with the same base, what's x? X has got to be negative 4. Because the x is here, and on this side we've got a negative 4, so just by observation we can say that x has to be negative 4. So for part B, can we write 27 and 9? Are both of those numbers in the same column? Yes. What's the base? 3. So we take 27, and instead of 27, we can write 3 cubed. We're still going to have, because it was 27 to the x, now we're going to have 3 cubed to the x. And on this side, instead of 9, I can write 3 squared. And since it was 9 to the 2x minus 1, I still have 2x minus 1 outside. Grade 9, exponent rules. What happens when you have an exponent to an exponent? Add, subtract, multiply, divide, give up? Multiply them. So this is the same as 3 to the 3x. And this side is the same as 3 to the 4x minus 2. Once you've got your bases the same, this one's not as straightforward as the last one. Do you see on the last one you could just go x is equal to minus 4. But on this one, we've got our bases the same. Does it make sense that what's in these red boxes has to be equal? If the equation itself is equal, then what is in those red boxes, because their 3's are the same, what's in those red boxes has to be equal. So you can write that out. I know that 3x has to equal 4x minus 2. And solving that isn't very hard. Move the 2 over to this side, move the 3x over to that side, and we get x is equal to 2. Three, 4, 5, and 6 are ones that you can do with this one.